All right, so some important stuff on the board. Your first exam is on Monday. It'll be in class unless you get university sanctioned accommodations. If that's true, you should have gotten an email from the testing center. Your test will be somewhere else. Show up, I will not be here. So there will be a substitute. You should treat with respect. She doesn't know what's going on. If you show up here to take the exam, you will have 75 minutes. Okay, so the accommodations are elsewhere. It will be chapter 16 through 18. I'll send you guys the study guide. The study guide is basically just going to be like what sections we didn't do, some odds and ends. I'll put these up. That column there that says no, obviously you have to know more than that. Like a 75-minute exam where you just have to know those 4 molecules would be pretty easy. But you need to know these by name, okay? So benzene itself, right? It's a 6-membered ring with 3 double bonds. And again, those 3 double bonds are critically important. 6-membered ring with no double bonds or 1 or 2 is not benzene. Then some, I don't want to make you guys memorize too much, and you'll sort of learn stuff as you need it in your career. But there are 3 compounds there that will make the rest of this class a little easier, and that you will run into from time to time, just kind of out in life. So toluene is one of them. It's pretty common. You can buy it at the hardware store. It's a pretty common paint remover. It's a good. So benzene itself is an amazing solvent. It's just like I said, it's carcinogenic, and we'll probably talk about why it's carcinogenic and why toluene isn't down the road. But been easy for a long, long time. You could buy this at the hardware store, and people used it at home, and it's a really common chemical to encounter. And then people realized it was kind of a decent carcinogen, and we phased that out. Toluene mostly replaced it, and toluene is a really pretty good replacement. It's not perfect, but this methyl group changes the chemistry a lot. Like I said, we will talk about this in the next segment. So toluene is a benzene with a single methyl group on it. Right, that raises the boiling point some. Benzene boils at about 80 degrees. Toluene boils at 110 degrees. You definitely don't have to memorize boiling points. Phenol is a really common disinfectant. You'll find it, I don't find it quite as much anymore, but there are, well, like Lysol, for example, there are quite a few disinfectants that all is in the name because of phenol. Lysol's not phenol anymore. Phenol's pretty harsh. But if you ever need to sterilize something, I don't know why this would happen, but you've got to sterilize something immediately, and you look around and there's a bottle of phenol sitting there. That'll work all right. And benzoic acid, you're going to encounter benzoic acid a lot more as the benzoate salt. So sodium benzoate appears as a preservative in a lot of compounds. Benzoate's pretty commonly found in the body. We'll talk about acid-base chemistry down the road. Right, the pH of your blood is between 7.35 and 7.45. I know that because you're all sitting there conscious and not collapsed. So if you put benzoic acid in a pH 7.4 situation, it will be benzoate, mostly benzoate. So you have to know the names of these 4 compounds. All right. So exam 1's Monday in class, 16 through 18. I'll send you a study guide by email either today or tomorrow. And then I'm doing a review session tomorrow evening in Salem 12 from 6:30 to 8 p.m. That attendance is not required. I won't take it. You won't impress me by coming. You won't impress me by not coming. I'm there to answer any questions you have. And it's questions only. I'm not going to lecture. I do tend to answer questions. I talked to a few people, like a lot of study sessions you go to because other people will have questions and you'll learn stuff, and that's a perfectly fine way to do it. But if I show up and nobody has any questions, I leave, right? So that's only happened one time that nobody had questions. Like people, I assume most of you have questions about organic chemistry at this point. So no, I'll be there. Any questions about any of that business?
Wait, so are you also going to tell us like what section?
Yes, you'll get that. And you'll get it before tomorrow's review session. Probably won't hear from me much after that. Okay, so the other thing to sort of, there are two reactions that I haven't covered that I will cover. Well, let me just put them up. I don't really like to do this way. You know, I've had lots of questions over time, sort of like, what do we have to know? If you didn't go over it in class, is it covered? And you know, use your, like, if I don't tell you a section's omitted, yeah, it's in principle on the test. I am going to, you know, when I write my exam, I'm pretty much going to focus on the stuff I talk in class about the stuff that I think is important. So if I've talked about it, certainly if I've talked about it at length, like, you should start there rather than, you know, finding the most obscure fact from the textbook. So I don't usually like to throw things like this just on the board, but it is important. These two will show up again, and we'll do a lot more redox chemistry down the road. So these are both reduction reactions. So as you look at organic molecules, so we would say this is a reduction reaction. You might remember from general chemistry, you can't have a reduction or an oxidation. They always go hand in hand. Sort of the same thing as acid-base chemistry, right? We always say acid-base chemistry. You can have a super strong acid just sit there completely innocent, minding its own business, not reacting with anything. For an acid to react, you have to have a base. For a base to react, you have to have an acid. So for something to be reduced, something else has to get oxidized. So they always go in pairs. And the thing that gains electrons, that is the thing that is reduced. The thing that loses electrons is oxidized. In organic chemistry, this usually gets, you usually see this by addition of a hydrogen. Right? So a hydrogen atom would be an H dot, right? A proton plus an electron. So you're really, if we add hydrogen to something, we're really adding electrons to it. And again, we're going to get into redox chemistry a lot, and then, you know, on exam 2, there will be a whole bunch of redox chemistry. These two reactions, as you know, I'm going out of order in the book, so these two reactions show up, and I'm just kind of throwing them on the board. So again, this is one of those things where I want you to know these, but, you know, there's not going to be a 20-point question on the exam that's this reaction I just threw up on the last day before the exam and mentioned in passing, right? I do want you to know it, but right now you kind of just have to commit it to memory. If you take a nitrobenzene, and you should know how to put a nitro on a benzene, if you treat that with iron or zinc metal in acid, you'll get a pretty complicated reaction where the NO2 group is reduced, right? So the nitrogen loses oxygen, gains hydrogen. That's a gain of electrons. The iron and the zinc then get oxidized, right? So those are the reducing agents. Likewise, if you have a carbonyl compound, if you have a carbonyl bond, sorry, this can be a ketone or an aldehyde. So this is going to be R is equal to C or H. So if you have a carbonyl and a ketone or an aldehyde, you treat that compound with zinc and mercury, and under acidic conditions, you basically just lop off the oxygen and add 2 hydrogens. Right? So that's a reduction. The other reaction that kind of goes the other way So if you have an alkyl group of some sort bonded to the benzene, and you treat this with potassium permanganate, you get an oxidation reaction. And whatever the group is here, that group, that the carbon bonded to the benzene gets oxidized all the way to a carboxylic acid. You will also see these sometimes written. So you will sometimes see a reduction just written as a bracket H, and you will see oxidations written as a bracket O. And like I said, on Monday, if by chance you need one of these reactions and you can't remember the reagents, but you're like, you know, I know that I can reduce this. If you write bracket H, you're not going to get 100% of the points, but you'll get most of it. Right? I want you to know that that's a reduction. Same thing down here if you need to oxidize something. The reason for most of this is that the benzylic position, this is just kind of a reminder. So there's a reaction you may have learned in Orgo 1. NBS is a reagent in bromosuccinimide. You might have seen, if you take a compound with a benzylic hydrogen, you treat it with NBS, you'll replace one of those hydrogens with a bromine. That's also an oxidation. So how does this work? I'm not going to go through the whole mechanism, but basically in this case, we get this radical. Right, this is called a benzylic radical. Got bad hands today. All right, why is that radical so stable? Supported by resonance. It is supported by resonance. So if you could draw, actually I tell you what, draw a resonance structure for that. Right, so if you look at the arrows I've drawn there, a benzylic position is any atom bonded to a benzene ring or an aromatic ring. Right, and that's usually going to be a carbon. And the point is, anything on that benzylic position, any electrons on that benzylic atom are going to be delocalized into the ring. So we've seen that with like an oxygen, right? If an oxygen has electrons on it, if an oxygen's bonded to a benzene, the oxygen has electrons, the oxygen is donating electrons by resonance. If there's an atom, a positively charged atom on the benzylic position, like a nitro, right, the electrons in the ring are being pulled out. So that works with a radical as well. If you haven't seen that, I am not going to ask you to draw any radical mechanisms on probably any exam this semester. But remember, the curved arrows we draw on a mechanism represent, like each bar represents an electron. So for these radical reactions, we can't, we sort of violate the rules. I don't like teaching you guys radical mechanisms until I know you have ionic mechanisms down, and that's usually not at the, a semester and a few lectures. But radical, I tell you in the beginning, right? Ionic mechanisms don't have arrows going different ways, don't have arrows going toward each other. That's because you can't put more than two electrons on an atom. But if we're just doing one electron at a time, we can do this. Right? So a pi bond can split, each electron goes to a different atom. This would get us this resonance structure. So maybe some of you drew that. That singly occupied orbital, right? That's a carbon radical. That carbon has 7 electrons, so it doesn't have a full octet. So it's formally it's electron poor, right? The carbon would like to have 8 electrons. So even though the atom is formally neutral, it would like to get another electron. All right. You can chase this singly occupied radical to here. So you might have drawn a resonance structure with an electron there and a double bond there. Then you can bring these electrons down with the radical there. And again, this is something you should see. Right. If I have a benzene, and whatever the characteristics of that atom Y, the characteristics of the atom at the benzylic position, you're going to have a little bit of Y character at the ortho and para positions. So if Y is electron rich, the ortho and para positions will be electron rich. If Y is electron poor, the ortho and para positions are electron poor. Does that make sense? So a benzylic radical is quite stable, a benzylic cation is quite stable, a benzylic anion is quite stable. And so you get a lot of chemistry on this benzylic position that you won't see anywhere else, right? If I take hexane and I treat it with potassium permanganate, nothing happens. None of the atoms in hexane are reactive enough to do anything with permanganate. But if it's a benzylic position, I treat it with permanganate. I'll even break carbon-carbon bonds here, right? So this could be like 20 carbons out to the right. Permanganate will oxidize this position all the way to the carboxylic acid. All right. Like I said, those are reactions I put up right at the end. You'll have some book problems that we'll see them, and they might help on the exam, might not. I want you to mostly focus on like resonance structures, thinking about mechanisms and predicting products of the reactions we've done. Sorry to put this right in front of you. But you might see a little bit of that down the road, and we certainly will use it in later sections. Yes.
So if you were like using this in context, so, like this is like your example from NO2 to NH2, would it be in the context of you wanted to add something and you wanted it to be directed?
Yeah, well, you'll actually see. We're going to do a problem here. Okay, so I'm going to try to get you guys a little more involved in the class now. That was me just like yapping at you. 57. Okay, so here's 3 reactions. I'm only drawing 1 reaction arrow, and what I mean is all 3 of your starting materials are treated with, so you might even do this in the same flask, right? Might put those 3 starting materials in the same flask. I dump some Br2 in. Let's see what we get. So your instructions are to predict the product and then rank the reactions in order of rate. So fastest to slowest. give me another. Well, actually, let's do the. Give me a second. I'm not angry with it. You got done with all that drawing mechanism for the top three. Okay, so what is notably missing from this reaction? There's no catalyst. Nor are there caps. All right, so if there's no catalyst, what does that mean? Can't add to the benzene ring. All right, so benzene rings, even a benzene that's electron rich like this, is not going to react with bromine unless there's a catalyst. The book mentions this. I don't like it because I think it diffuses matter. That's not altogether true, right? So, there are things in science that are like, we have like really sound theories. Like if I break one of those windows and hold a rock out and drop it, it's going to fall. All right. What we don't know for absolute certain is why it's going to fall. We think we do, right? We have a really good explanation. I mean, and we have had for 400 or 500 years, like Newton did all the math. We have a theory of gravitation. Einstein came around and said, no, that's not quite right. Tweaked it a little bit. We have a better idea. We're still not. Like, is that true? That might change. Like, our explanation for why a rock held out a window will fall to the ground might change. What won't change is the fact that if I hold a rock out the window, it's going to fall to the ground. All right. So that is an empirical fact. There is no theory here that says bromine can't add to the benzene no matter what. Right? What we find is benzenes tend to be stable enough that they don't react with bromine without a catalyst. And that's what I would like you guys to learn. Right? But it is one of these things where there are exceptions. And so the book does one where it takes phenol, and sure enough, if you treat phenol with bromine, you wind up with, if you treat it with enough bromine, you get a bromine at both ortho positions and the parent position. Like phenol's super electron rich. You can lose this hydrogen that can make it more electron rich. So that's an exception. And I would like not to bog you guys down with a lot of exceptions. Okay, so as you're reading the book, it's a book, so it's got to be complete. If I was writing the book, I'd do the same thing. I would type out aromatic molecules don't react with electrophiles unless there's a catalyst. And then, being a professional organic chemist, I'd be, oh, well, there's that one, and there's this other one. Oh, and sometimes this. And that's all. If you guys ever become a professional organic chemist, you should learn all this. All right. Right now, what I want you guys is to learn patterns. The pattern is these benzenes are not going to react with an electrophile unless there's a catalyst. Okay, so if the benzene doesn't react, what reacts? The alkene. Does anything have to react? If I mix chemicals together, does something have to happen? No. In this case, it does. You guys remember from chapter 8, right? If I have an alkene, it'll react with bromine. It'll add a BR to both carbons of the double bond. That will be an anti-addition, so the two BRs will end up trans if there's stereochemistry. There is not stereochemistry here, right? Well, there's some, but the two bromines can't be cis or trans because there's two hydrogens on this carbon. You'd never be able to tell, right? The molecule's rotating a few hundred million times a second around this bond. There's no way to ever tell if the two BRs are cis or trans or anti. What would the stereochemistry here be? Tetrahedral. So that bromine's got to be out or back. Would I have it all out, all back? The mix? Let's think about that. For that, you need mechanism. All right, so that's going to be the product for all of these. No. All right, the only thing that's changing is what's on the benzene. But what happens to the alkene is the same in every one of these. Well, maybe I gave you too much time. I don't know. How do we get to a relative rate? What do we need to, what do we really have to know about this reaction in order to do relative rate? So one, you have to know how the electronics of the alkene are affected by the substituents, right? Because that's going to be the change. Everything is the same except what's para to the alkene. So this molecule in the middle, you don't have to know this one, but this is called styrene. Yeah, again, you guys hear the word styrene fairly often. Well, you know, for how much you hear about chemicals. Polystyrene. So polystyrene is made by taking styrene and polymer. Okay, so in styrene, the para group is a hydrogen, and again, that's always kind of going to be our rate equals 1. Is methoxy donating or withdrawing? All right, it's donating. Nitro is withdrawing or donating. All right. So we have an electron-rich aromatic ring, and so what I've told you guys so far, right? We've talked about methoxys, nitros, substituents donating or withdrawing from the benzene. Is this double bond conjugated or not to the benzene? Conjugated, right? So you've got the double bond, one sigma bond, then a benzene. So the pi bond on the alkene is part of a larger pi system. That's one conjugated pi system. The other thing you have to know is not just the electronics of the substituent, you have to know the mechanism. So this pi system is more electron rich than that one, and that one's more electron rich than that one. So of our three, this one is the most electron rich pi system. This one is the least. All right. But that doesn't tell you anything about, I mean, it's an important piece to know for ranking the rate. What we have to know is the pi system being a nucleophile or an electrophile? All right. If the pi system is a nucleophile, a Lewis base, an electron donor, that'll be the fastest. If the pi system is an electron acceptor, this one will be the fastest, right? Makes sense. So in this reaction, is the pi system donating electrons or receiving electrons? Got one vote for donating. That's not a quorum. All right, everybody's going to go with that. So if you don't remember this, let's do the mechanism from back in the day. And so bromine is a non-polar molecule. The bromine-bromine bond is quite weak. That's true of all the halogens. That's why the halogens are toxic. The halogens are electronegative atoms, but the bond also breaks really easily, right? So fluorine and chlorine will kill you. Fluorine really fast, chlorine relatively slower. So if you've read any history of World War I, chlorine gas was used on the battlefield. It's a great story. If you're into history of chemistry, I teach a class called history of chemistry, not to advertise or anything. But there's a guy named Fritz Haber. Anybody heard of him? All right, won a Nobel Prize. He's why there are 8 billion of us instead of 3 billion of us. I shouldn't say that. Nobody's that important. But Haber won the Nobel Prize along with a guy named Bosch in the he won the 1918 Nobel Prize for his discovery in 1909. He figured out how to turn nitrogen gas in the air into ammonia in an economical fashion. All right, so we need ammonia to grow food. Before that, the way we fertilized crops was shit. All right, pardon the French, but that's the technical term. All right, so some of it back in the Middle Ages, it was human. Then people were like, this is miserable. And they started harvesting like things like guano. We like took the islands off the west coast of South America were just filled with birds. And Europeans actually went down there and just like, you know, the people who had been living there were like, okay, that island's covered in bird poo, let's leave it alone. And the Europeans like sailed down there, lots of them died, so that they could fill their holes with bird food, bring it back to Europe. All right. We were not progressing all out as a people, as a human civilization, right? You can't support billions of people on bird food, or even humans. So once we figured out how to turn air into fertilizer, population exploded. There were other things like antibiotics and all that. The other thing Haber did that was interesting is during World War I, he figured out that, you know, if you like blow chlorine gas across the French lines, they'll all die. Anyway, people were very unhappy when he won the 1918 Nobel Prize because he just gassed a whole bunch of people. By the way, and then I'll shut up, chemical weapons are ridiculous, okay? They're a terrible way of killing people. Chlorine gas, what does chlorine gas do? If I like just open a hose of chlorine gas out the window, what happens? What's that? Why would my blowing it out the window? I'm in here. Why would my lungs get burned? People maybe, but they're down there. Like here, a lot of it would go up. But my lungs might get burned. Why is that? Could sink. So what it depends, where I'm trying to go with this, sorry. I'm glad that you guys don't sit around thinking about, what if I blew chlorine gas all over? You will as you get older, all right? You'll be in a meeting someday and this will come back to you and you're like, what if I filled this room with chlorine gas? Can I go home if I do this? Chlorine can sink, it's heavier than air. But the other thing is there's wind. So the very first time they did this, they literally just like rolled tanks of chlorine out, opened the thing and ran. And the wind shifted and blew it all back into the German. So some people believe in karma. That's good. They got more sophisticated. They eventually made things that were way worse. They liberated chlorine gas easier. We got tear gas out of that. All sorts of cool things. Nobody ever thought to use fluorine because fluorine is just, you can't even put it in that tank. Fluorine is so reactive and corrosive, it's hard to handle. And nobody would think I can open the valve and run. Like I open that valve, I die. So people who do fluorine chemistry are very skilled and a little crazy. Move down, bromine, which we're using here. This bromine-bromine bond breaks super easy. And bromine actually does this reaction the best. Like if you have to put a halogen on an organic molecule, bromine's the one to use. Not all that talk. It's also a liquid, not a gas, by far. So if you like my little anecdotes, listen to this. Chemical safety, by far, liquids are safer than gases. Solids are safer than liquids. All right, gases go wherever gases go. You can't always see them. Liquids you can kind of control, but they splash and they can go through your skin. Solids, I can just dump the solid there. I'm not breathing it. You know, poisons have to get into your body. So there has to be a mechanism for that. Solids you essentially have to intentionally ingest, or somebody has to slip it into your food. Again. So liquids you might be handling in splash. You guys will see this in lab, right? You're using bleach this week. Track that. You know, look at your lab coat. You will notice if you spill bleach on them, right? A lot of my shirts have like colorless spots on them because I don't like to wear a lab coat and I spill bleach. So liquids can spill. Gases are really hazardous. So chlorine and chlorine, we try not to work with. Bromine is a really good lab reagent. Iodine, you will see iodine used if you've ever had a surgery or you know, even something minor, they'll like just lather you up with iodine. It's reactive enough that bond breaks, it does stuff like this. It'll kill cells. Won't go through skin the way bromine will, but it's not so reactive that it burns you. Bromine will blister your skin if you get it on you. Like bromine is not harmless. It's just not nearly as reactive as chlorine. How the hell? All right. Sorry, you guys have an exam to worry about. I'm like talking about the Secret Service, and I'm in here talking about chemical weapons. All right. So reaction here, the mechanism, the first step of this mechanism is this. All right, bromine is nonpolar. The two bromines have identical electronegativity, but the electrons move constantly in these molecules. So you get instantaneous dipoles. The molecule can be polarized by electrons. Right? You've got a pi system here that's got fairly high energy reactive electrons. They can polarize the bromine-bromine bond. I'm going to erase our product. And then we get this weird intermediate that you may remember. Hopefully you remember. Get a ammonium cation and a bromonium anion. Right? And not a bromonium anion, a bromine. We get a bromonium cation and a bromine. All right. So the next step, right? If you look at this product, you got to get a PR on that carbon, and well, we're there, right? Hallelujah. But we can't end up with two bonds there. So the bromide attacks the left substituted. And it does that, it's like an SN2 reaction. The bromide comes from behind, that CBR bond, and we get our product. What sets the stereochemistry here, right? That is a chiral center. That carbon has 4 substituents on it. Got a hydrogen, a bromine, CH2, and a benzene. 4 different things. So that could be R or S. And what sets that chemistry is, right? I've drawn it like this. This looks like all these molecules are in the plane of the board, but that is not what would happen. All right. The pi bond, let's say the pi system stays in the plane of the board. This Br2 would either come from above, so the pi electrons would attack this way, or it could come from the back of the board. Pi electrons would go that way. The Br would wind up back. There is no reason for there to be a preference there. I mean, obviously, if it was really the board and a wall behind it, the bromine would come this way, right? The bromine would wind up out. But we're representing this. This thing's floating around in solution. There's nothing that makes the back different from the front. So you wind up here with 0% EV, a racemic mixture, 50% R, 50% S. Sorry, folks at home. Okay, the other thing to look at here, the pi system is the nucleophile, or the Lewis base. It's the electron donor. And you know this because in your mechanism, the arrows are going away from it. So watch this. You can do this. I've drawn the arrow away from that double bond, but I could also do this. Everybody watching? This is a neat trick. A long pair there. Bang, bang, bang. Right? That methoxy is pushing electrons not just into the benzene, but into the alkene. And the arrows that you would draw for the resonance structure line up nicely for the arrows that you would draw for the mechanism. Right? So this is going to be our fastest reaction. And then this has to be our slowest reaction. And if you think about this, let me draw this nitro out. Right, that nitrogen is positive. If I was going to draw a resonance structure here, it would be like that, toward the oxygen. And then in my mechanism, this arrow needs to go the other way. So that nitro is in fact having the opposite effect. It's actually taking electrons away from the alkene. That makes that alkene less able to give them away. So you guys can't memorize that an electron donating group makes reactions go faster. Right? An electron donating group makes nucleophiles more nucleophilic. So an electrophilic aromatic substitution, yeah, the electron donor is going to make the reaction faster. But an electron withdrawing group makes the pi system more electron poor, makes it more electrophilic. So in any reaction where the pi system needs to be an electrophile, an electron withdrawing group makes the reaction faster. So and it's at this point that I see a lot of people just try to memorize electron donor is faster, electron withdrawing group is slower. So electrophilic aromatic substitution, yes, that works really well. And you might get the questions on Monday like, then on exam 2, all of a sudden the pi bond is mostly an electrophile and you'll be practically split up. So try to learn it right the first time. I mean, that's always, I know you're trying to do it, sorry. All right, we're gonna have to go a little faster on this one. All right, this reaction gives one single product. What is it and why? Give you all another couple of minutes on the addition of HBr. If you've done that one and you're happy with it, you can try the synthesis I've shown you down there. All right, so I'm gonna come back over. I know I gave you a synthesis, but tear yourself away from that and come back over here. So the addition of HBr, you guys have seen this as a 1-2 versus a 1-4 addition problem. And again, I don't want to take away from stuff you've memorized. Like memorization is important. You know, you guys have been through a lot of education at this point. You know that there are educational philosophies and educators are always talking about this stuff. And at some point, like the 90s, we all decided we're doing probably before that, we all decided we're doing way too much memorization. What we're trying to educate people for changes based on where we are. So 120 years ago, we didn't have computers. It wasn't easy. You know, people didn't have big libraries. Memorization was really important. If you were going to go out in the world, right, you might be somewhere and you might really have to know all this stuff just like in your head. And so they did crazy things, right? Like you would have to memorize 4-page poems and stuff, right? And some of that was the, you know, shared culture, but a lot of that was teaching you how to memorize stuff. As memorization has become less important, right? We all have basically all of human knowledge in our phones, drop of a hat. We don't teach that as much. And we actually got to a point where we're like, you don't have to know, don't memorize anything. Memorization's bad. Okay, again, that's clearly not right. You have to have some stuff in your head. So a lot of you have probably, you know, memorized 1-2 versus 1-4. 1-2 is kinetic, 1-4 is thermodynamic. And like I said, that's the way to bet. But it is not always true. The kinetic product forms fastest. The thermodynamic product is the most stable. Okay? That's what you should memorize. Kinetic product forms fastest. Thermodynamic product is the most stable product. And as we talked about at that point, if the thermodynamic product, or sorry, if the kinetic product is also the thermodynamic product, it's just the product. So in this case, did they ever make people sit here? That was fun. Sorry. All right, so this is the 1-2 product. The only one that forms. How come? Why is this also the thermodynamic product? So draw out the other things you could get. You could get another 1-2 product here. Well, actually, this becomes hard. All right, I think there's another 1-4. Anyway, look at the stability of this alkene versus the other alkenes. Which one of those looks most stable? I mean, it's kind of given to you, right? Like the product I drew is the most, why is it the most stable? Yeah, so two things you're going to look at for alkene stability. One is how substituted is it? Right, the more things you have bonded that aren't H, the more stable the alkene tends to be. The other is it conjugated or not? In none of these other products is the pi bond conjugated. The only pi bond that's conjugated to the benzene is in that top one. So if we think about what we get here, right? The other reason you look at this cation, we're going to get not just the cation, we're going to get the diene is not symmetric. So the cation we're going to get normally you could get, like if this was just a methyl group, we could get the cation on either end. We could do 1, 2 on either end. But here, this, right, this is now a benzylic cation. It's delocalized. Let me back up. This cation is delocalized over 3 atoms bonded to the benzene and the benzene. Right? So now the bromine can attack either one of these. Attack there, and attack there. And again, the kinetic product, the bromine is down on this end, right? The proton went there. The proton that we added went out here on the end. The Br is sitting next to it, so the Br can attack here fastest. So the kinetic product would be this one. And then the other thing is that double bond is conjugated. That double bond is conjugated to the alkene. And so it's the most thermodynamic. So even if the reaction reverses, right? So we get to here, that's a reversible process. Even if it reverses, the molecule would rather have its double bond conjugated to the benzene than out here by itself. So, like I said, there are exceptions to every rule. Some rule, most rules. 1, 2 is essentially always going to be the kinetic product. 1, 4 will usually be the thermodynamic product, but not necessarily. The thermodynamic product is the most stable product. So always judge stability. And I get that at this point, if you guys miss like why a molecule is more stable than the other, that's kind of okay. Like that's a lot of what you're learning in this class is how these structures, how the lines that we draw affect stability. Just don't lose sight of the fact you can't just assume 1, 4 has to be the most stable product. Usually is, but not always. You're fine. Questions about that? Okay, so now work on this synthesis I put up on the board. If you're at home, oh, that was shaky. So here's what this is doing. You may have already looked at. I mean, there's problems like this assigned in the textbook, and there are problems like this on the old test. We're going to start with benzene, and we're going to make this molecule. And you got to figure out how to do that. And you might think it's easy, but it's not. It's not terribly difficult. It's not 100% straightforward. And if you've gotten that one, I'll put one up over there. The other thing, usually these questions will say something like using any other reagents you want. As we go forward in this class, synthesis questions will get more limitations put on. Like I might say, starting with X and ethanol, make this molecule. Right, so all the carbons have to come from benzene. Basically, this benzene ring has to come from benzene. No, there's a good question. That's a good question in terms of like business of the class. As you're doing these, like it's probably not a terrible idea to draw a mechanism, right? Like if you're studying at home and you do a reaction, like do more than is asked. However, on the exam, when do you have to draw a resonance structure? You have to draw a resonance structure when the question says draw a resonance structure, right? So if I say, draw the product of this rate, there will be, I'm not giving anything away on this. There will be a question like, here's a whole bunch of reactions, draw the product. What it says is draw the product. You don't have to draw resonance structures. You don't have to draw mechanisms. You don't have to draw reaction energy diagrams. You just have to draw the product. Now, on your scratch paper, maybe you need to draw a mechanism. Maybe you do that on the page. Like, so on that question in particular, if you draw a screwy mechanism and the right product, you will get full credit. I might point at the mechanism and say, this is screwy, like this won't work this way. The other thing then is if you get the product wrong and you've got a screwy mechanism, I might be able to say, here's why you got the wrong product, you did something wrong here. Like in terms of me interpreting what you're doing, I won't give you partial credit for it, but it might help me like coach you to be better. Now there will also be questions, again, I'm not giving anything away, where I say draw the mechanism for this reaction. If it says draw a mechanism, I mean the full mechanism. You got to draw curved arrows. You got to show all the intermediates. Like I want a mechanism. If I say draw a reaction energy diagram, I don't mean half-assed and just sort of, draw a wavy line. Like you got to actually think about energy of intermediates. So we'll get on to, like I said, when you're practicing a book problem or something, it says predict the product, draw the mechanism. Also on the mechanisms, I don't hold you guys responsible for coming up with the electrophile for any of these. So Br2 and iron, you get essentially Br plus to Br minus. Okay, so on this synthesis, what do you have to think about? Like, well, you got to know, like, look at the bonds that have to get made. You have to make a carbon chloride bond. You have to make a carbon nitrogen bond. How do you know to do that? Well, if I start with benzene, Cl2 and aluminum chloride, say, that will give me chlorobenzene. And then I know if I start with benzene and I use nitric acid and sulfuric acid, I get a nitro group, right? So you know the two reactions you need. And like you guys have to know those reactions. So what's challenging about this problem?
Yeah.
Right. You've got two reactions. You're going to do these two reactions in a synthesis, right? You got to put a nitro on, you got to put a chlorine on. Both these reactions are going to appear. What you have to figure out is the order they appear. And for that, you have to figure out where these things direct. So nitro is a meta-director, chlorine is an ortho-para-director, right? Chlorine is the exception, it slows the reaction down, but it's an ortho-para-director. And so are these ortho, meta, or para? They're meta. So the name of this compound would be metachloro nitrobenzene. Right? And you've got to put the meta director on first. So the synthesis will look like this. And so there's your nitro, and then so right, if I wanted to do this purely in terms of reaction rate, I'd put the nitro on second. Nitro is more electron withdrawing than chlorine. So if I could put the chlorine on first and then nitrate it, that would go faster. But it would go in the wrong place. I'd get para nitro. I would get the two groups of para if I put chlorine on first. Yeah.
It's not like something like say they amount would you like would be their amount. So
if it literally doesn't matter, no.
Does
Right.
Even if one.
Oh, well, no, so if, so say the two groups are para, but one of them's a chlorine, like you'd put the activator on first,
And if we did it the other way.
you'd lose some points. Like a lot of times my question will say, show the best. And the same thing is true there. You got to think of asterisk. I get a lot of questions about, like, let's say a group's an ortho pair director. If I put it on and I want to group ortho to it, and then a group para to it, doesn't matter which order. And it does actually. You're going to get, like, especially if there's a lot of sterics. Like if I have a bulky ortho para director, I'm going to go para rather than, but it wouldn't be full.
Take 1 minute, I'll give you 1 entire minute.
Maybe this other synthesis question, that should be easy, like, you probably already have it. Probably woke up this morning thinking about this. I respect the people that aren't even trying. I just want to make sure I finish talking about it. So you guys should definitely, there's some synthesis problems recommended in the textbook, definitely try those. The couple on the old exam.
Did you know like CO2 over FD? I know we did.
Yeah. So that's one, like, I use aluminum chloride. I like aluminum chloride. It's one of my favorite reagents. Gives off HCl really well, makes your nose tickle. Iron chloride, it turns gummy. I don't like it. But you could have used aluminum metal, you could have used iron metal, you could have used iron chloride. You could have used the other thing is we teach you guys a few reagents. Like if we threw every reagent at you, it would not be fair. It isn't. I don't know all the reagents. Okay, so if you're looking at this, if you thought about it, right? So you know how to, well, let's do ortho pair. Is this an ortho pair director or meta? This one is a meta director. That's probably not going on first, right?
No.
Is this ortho pair?
Ortho pair.
Yeah, so, all right, so we know how to put that carbonyl on. This one really does have to be aluminum chloride. Again, this is not one I'm going to be a pain in the ass about. If you wrote iron chloride here, okay. This reaction really needs to be aluminum though. But that's kind of a trick of the trade. How do I put an epoxy? What's my source of this? Like what you would need, right? To do electrophilic aromatic substitution is that. But then the oxygen's not electrophilic, right? So what reaction would I be doing? Right. So you guys don't know our reagents that will do that. So the trick to this problem is it looks deceptively simple. It looks like this other one. There's two things on there, so I'm just gonna put that on there. This does not exist. Really? So what you would want here, if you're going to put a methoxy on, you're going to want this reagent. Could be a lithium, could be a potassium. What it can't be is methanol. Right? Methanol is not a good nuclear bond. Methanol is a weak nuclear bond. So then, what you would need to do is that's how you know to put an oxygen. What do you have to do a nucleophilic aromatic substitution? Right. You gotta have a lead group. What else? You have to have an electron withdrawing group somewhere. So we either need an electron withdrawing group here or ortho two. Right. So the nucleophilic aromatic substitution, you know, leaving group ortho to an electron withdrawing group or para to an electron withdrawing. Right. So what leaving groups do you know how to put on? the halogens, right? You can put on chlorine, bromine, iodine. Chlorine's the best one in this particular reaction. So you'd want to do that. Chlorine and electron, or sorry, well, let's do that. Chlorine electron donor or withdrawal? Yeah. How do you mean that? It withdraws in terms of rate, donating in terms of ortho-para meta. All right, so given all the information here, see if you can come up with a sentence. Take a couple of minutes to put those, to try to assemble those reactions in an order that would give you the product.
Are we trying to get the chlorine on first?
Maybe, yeah. Yeah. What you're trying to do is go from benzene to this molecule over here.
Okay.
Anybody recognize the molecule on the upper right, by the way? Yeah, I literally just recognized that myself. I did not, when I drew this up, I didn't mean it to be elegant. It's just, when you're such a good teacher, it just happens, these things just. I should have got more loud. Yeah, because you need a nucleophile. So. Right, the nucleophile has to attack there, right? And then the electrons would go there, for instance. They would go there, or they might go and make a pi bond, and then the electrons go there. So having an electron withdrawing group there. So your intermediate becomes that, right? Where this is a negative charge. That negative charge is stabilized by the electron withdrawal. So that negative charge never ends up there. So if the electron withdrawing group is meta to the leaving group, a nucleophile attacking the carbon of the leaving group can never, that anion can never be stabilized. We can talk about it more. Okay, so 5 minutes to go. I'm just going to put the reactions up. So yes, you put chlorine on first. So the first thing to do here, chlorine, and again, iron, aluminum chloride, iron chloride, whatever you want. Put the chlorine in, then we do acetyl chloride and aluminum. This is just the Friedel-Crafts. This is not a great reaction. Again, the book really harps on don't do Friedel-Crafts unless you have an electron donor. And that's, I mean, again, if you came to my lab and we actually needed to make this molecule, we'd probably choose to do that. But if you can't make it go, for me in this class, you can make it go. So now we have the leaving group para to the electron withdrawing group. And then you use sodium methoxide. And I'm going to write methanol there, right? You need a solvent. Actually, the way you make sodium methoxide, you take methanol and you drop chunks of sodium into it. A lot of fun to do. And then, so this is an electrophilic aromatic substitution. Second step is electrophilic aromatic substitution. Third step is a nucleophilic aromatic substitution. That gets you your product. Right. So like I said, if you basically at this point, right, synthesis problems are going to draw on, it's either going to be a Diels-Alder, it might be a 1,2,1,4-diene. Those are harder to use. The Diels-Alder, or if it's chapter 18, you know, you've got a set of reagents that you're supposed to know how to put on a benzene ring with electrophilic aromatic substitution. If there's something there that isn't that, you've got to do something else. So it could be nucleophilic aromatic substitution. It could be the reaction I showed you. Like you could put like you had an NH2 group on here somewhere. Or was I? Like if I had said this needs to be an NH2, You guys don't know how to put an H2 on using electrophilic aromatic substitution. So you'd have to reduce, you'd put the NO2 on and then you'd reduce.
Sorry, no, the OCH.
Yep.
Could you not have done like a single fast and did like CH3, like an extra, like a CL on the end? You know,
So you have
like if you did like,
that.
like,
Yeah, so that's,
or is that like not?
you know how I'm telling you that, I was asked if you could use that reagent. Yeah, this is one of those things where I tell you guys, like, I want you to learn patterns and I want you to memorize everything. This is one of those. So that's also kind of from lab today. Bleach is this molecule. Right, so that's bleach, sodium hypochlorite. Actually, I guess O minus sodium. The sodium salt of that would be bleach. Really reactive. And this bond, the reason bleach kills almost everything is that bond is super unstable. That means is you really can't get that molecule. Is that something you should know? No, probably not. Well, it is now, she asked. So, no, it's good. And it's a good question. Like in terms of seeing patterns, yeah, I'd want you to ask that question. Like, why can't we do that? For Frito crafts, so Frito crafts is like, basically this, right? R has to be an alkyl group or an acyl group. So CH, whatever, and right, even that needs to be a carbon. So basically, you can't have a chloride bonded to a carbonyl and then other heteroatoms. And you can't have the chloride for the Friedel-Crafts alkylation. You can't have the chloride be bonded to anything but a carbon. It's got to be. I guess the easier way to say that instead of drawing all that stuff, it's got to be a carbocation. Questions? We don't have a minute. Okay, so again, review session. I'm in lab today, so if you're not in my lab, hang on just 1 second. I know you got a bus to catch. If you're not in my lab, if you let me get lab started and you have a question, I can answer it. And if you're in my lab, certainly once we get going, like do your lab, but we can talk about stuff while that's happening. I'll be in Salem 12 tomorrow night, and then I wish you well. Yeah, class is over. That's an easier way of saying that. And you want to talk about this real quick? Yeah. Hope everybody's feeling okay at home. See ya.